Okay, question number one. If you were in a spaceship and fired a cannonball into space, how much force would have to be exerted on the ball to keep it moving once it has left the spaceship? And your choices are A, it depends on the mass of the ball, B, it depends on the speed of the spaceship, C, no force would be required, or D, there's not enough information to answer this question. So, again, the point of this is that it's in space. And so what does space not have that we have here on Earth? And the idea is that there is no gravity and there is no air resistance. So if this spaceship fires a cannonball, for some reason they have cannon technology still, but they can create a spaceship. This ball leaves the spaceship for some reason, it's shot out somehow. But once it leaves the spaceship is no longer exerting a force on it. And so what that means is you have no net force. Because there's no gravity or air resistance either. The sum of the forces equals 0. Therefore, you have no acceleration. And if you have no acceleration, that means it's not going to speed up, it's not going to slow down, it's not going to change direction. It will continue to do the thing that it was already doing without a force. So there will be no force required to keep it moving. All right, moving on to number 2. Many automobile passengers have suffered neck injuries when struck by cars from behind. How does Newton's law of inertia apply here? Please watch the next video.
Safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Number 3, suppose you place a ball in the middle of a wagon and then accelerate the wagon forward. The ball will A, appear to stay in the middle of the wagon, B, appear to move toward the front of the wagon, C, appear to move toward the back of the wagon, or D, it depends on the mass of the ball. Again, please watch the following video.
Go.
Number 4, if an elephant were chasing you, its enormous mass would be most threatening, but if you zigzagged, its mass would be to your advantage. Why? A, because it's so massive it couldn't run as fast as you. All right, that is not true. Elephants can run faster than you. B, because it's so massive, it would be harder for the elephant to change direction. That is the correct answer. It can get its speed going in one direction, but to change then requires even more force. If you've ever seen a large bird flying, soaring like an eagle, and little sparrows kind of harassing it, bouncing in and hitting it, they can move around really quickly. They can't fly as fast as the eagle can in one direction, but they are more maneuverable because of their smaller mass. It's the same thing. An elephant could not change direction. So if you're running from an elephant, run in a serpentine motion. Number 5. 2 closed containers look the same, but one is packed with lead and the other with a few feathers. How could you determine which has more mass if you and the containers were orbiting in a weightless condition in outer space? A, put the canisters on a scale and weigh them. B, shake the canisters. The one that's harder to shake back and forth is more massive. C, shake the canisters. The one that is easier to shake back and forth and more massive. Or D, there is no way of knowing this. Well, for A, you can't put the canisters on a scale and weigh them because there is no normal force. There's no preferred direction for something to land. The scale would float. So you can't do that. The answer is B, shake the canisters, and the one that's harder to shake back and forth is the more massive. Even though there is no weight present, or it seems weightless anyway, Newton's law of inertia still applies. So something with more mass is more difficult to move. It has more inertia, therefore it has more of a tendency to keep on doing what it's already doing. Please see the following video. All right, here in the magic of my basement, I have 2 floating milk jugs. One of them is full of water, The other one is only full of air. How do we know which is which? You are not allowed to lift them up. But what can we do? What if I go and flick it with my finger? This one barely moves at all. Why? Because it has a greater mass. All right, moving on to number 6. A metal ball is put into the end of a tube indicated by the arrow. The ball is then shot out of the other end of the tube at high speed. Pick the path the ball will follow after it exits the tube. Note you're looking down on these tubes. They are not vertical. Please watch the following video. All right, now that you've seen the video, which one would you pick? Hopefully you're going to pick C because you just saw it happen. And again, think about what's going on here. You've got the ball going through the tube. Why does the ball follow a circular path anyway? Because the tube wall is making that happen. Once it leaves the tube wall, it doesn't have a force pushing it on it anymore to keep going in that path. So it's going to keep doing what it was already doing at the moment that it left the tube. So at this moment, right here, the ball is going that direction. Right here, the ball is going this direction. Right here, the ball is going this direction. And right here, the ball is going this direction. And now there's no more tube to keep it going in that circle. So it's just going to keep going in the direction it was going. All right, moving right along to number 7. How much support force does a table exert on a book that weighs 15 newtons when the book is placed on the table? A, it depends on the kind of table. B, 15 newtons. C, less than 15 newtons. Or D, more than 15 newtons. All right, so here's my table. And here's the book. And the book has a weight of 15 newtons, which means there is a downward pull of 15 newtons. Now, if that was the only force on the book, it would have to be accelerating downward. But we know that it's just sitting still on the table, therefore its acceleration is 0, therefore the net force is 0. So there must be some upward force pushing on it. Now, what do we call that upward force that things provide? We call that the normal force. And so then the question is, what is the normal force? Well, we know that these forces are balanced, so therefore the normal force, I'll just represent that with Fn, must equal, that's the upward force, must equal the downward force of gravity. And therefore Fn equals 15, that's our answer. All right, moving on to number 8. What if a hand pushes down on the book with a force of 20 newtons? All right, so once again, here's my table. Here's the book. And now it still has the 15 newtons of force from the earth pulling down on it, but in addition, now you're pushing down on it with 20 more newtons. So it's still not moving, therefore there must be an upward force. Again, we call this the normal force. We'll just keep using that term. We know that the upward force, which we call the normal force, is equal to the downward force, which is 15 newtons plus 20 newtons. So add those together, and that's 35 newtons is our upward normal force. Okay, moving right along, last question for this particular assignment. What if a rope lifts up on the book with a force of 10 newtons? I'm going to not draw the table this time, and I'm not even going to draw the book. I'm just going to draw a dot like I would do for a proper free body diagram. And so, again, what forces do we have? We have a downward force of 15 newtons. That is always going to be there. That's the weight of the book. Now it says a rope is lifting up on it with a force of 10 newtons. All right, so that's not enough force to lift the book up. However, the table doesn't have to hold the book up as much anymore. The upward force still needs to equal the downward force. So there must be one more force here from the table, that normal force, So we've got two upward forces, the normal force and the upward force of the person pulling with the rope. And we have the downward force of the weight this time, 15. So what plus 10 equals 15? That means our normal force must be 5 newtons, and that is answer C. All right.